Section 3.1, Basic Concepts of Probability and Counting. Let's start the section. Start with the definition of a probability experiment, an outcome, sample space, and event. The probability experiment is an action or a trial through which specific results, such as count, measurements, or responses, are obtained. The result of a single trial is the probability an event is an outcome. The set of all possible outcomes of a probability experiment is the sample space, and the event is a subset of a sample space. It may consist of one or more outcomes. Let's see an example. A survey consists of asking people for their blood types, O, A, and AB, including whether they are Rh positive or Rh negative, meaning positive or negative. This might make you think of your own blood type, right? Determine the number of outcomes and identify the sample space. Okay, so here we have all our outcomes. We can have O, A, B, or AB for our blood types. Now for each one, there's a possibility of being positive or negative. So therefore we see that we can be O positive or negative, A positive, A negative, B positive, B negative, AB positive, and AB negative. All right, so again, these are all of our possibilities. And because they're all of our possibilities, these are our sample space. So to answer your question, what is our sample space? It would be all of those answers. So we have O positive or negative, A positive or negative, B positive or negative, and AB positive and negative. Moving forward. So for the previous problem, we did a tree to create our sample space, but that's not always the most convenient way to go about it. So let's learn about different ways. The fundamental counting principle. In example 1, we can see all the outcomes which create our sample space. But in other situations, our sample space may be too big and not worth the effort to draw out. How do we come up with the sample space? We can use the fundamental counting principle. Definition of the fundamental counting principle. If one event can occur in m ways, and a second event can occur in n ways, the number of ways the two events can occur in sequence is m times n ways. This rule can be extended to any number of events occurring in sequence. Let's see an example. You are purchasing a new car. The possible manufacturers, car size, and colors are listed in the table. How many ways can you select one manufacturer, one car size, and one color? So what are all the ways it can list all this out? So if we were to do a factor tree, so you would start out with manufacturer, which would give us Ford, GM, and Honda. All right, for Ford, we can pick either compact or midsize. And then for each one, we give 4 options. That's already a lot, and I still have to do it 2 more times, right? So we can have white, red, black, green, white, red, black, and green. So this one isn't so bad. We can actually do this one all the way. But you can see how just by adding an extra category, it would be much more. I mean, what if we also added from Honda, we added another brand or another type of car like a minivan or a truck, right? So counting principle makes this easier. By using the counting principle, you just multiply our options. We have 3 manufacturers, 2 options for car size, and 4 colors. So it'd be 3 times 2 times 4. We get 24 different car options. Example 4. The access code for our car security system consists of 4 digits. Each digit can be any number from 0 through 9. How many access codes are possible? Okay, let's see our options. For 1, each digit can be used only once and not repeated. All right, so using our counting principle, I want to find out 4 options. 1, 2, 3, 4, and each number can only be used once, not repeated. So just to emphasize, when we see numbers 0 through 9, that includes numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 different numbers. So for my first number, I have 10 options. For my second number, I already used one, so I will only have one less option, so I will have 9. And then 8, and then 7. So we multiply all of that out, we get 5,040. I can create 5,040 different ways of creating a 4-digit number. All right, 2. Each digit can be repeated. Okay, if each digit for my 4-digit code can be repeated, that would be 10 times 10 times 10 times 10. Or if you want to use exponential notation, 10 to the 4th power, which gives us 10,000 combinations. Third one, each digit can be repeated, but the first digit cannot be 0 or 1. So 1, 2, 3, 4. So my first digit cannot be 0 or 1. So from our 10 options, I'm taking away 2 different options, 0 and 1. So that would give us 8 times 10 times 10 times 10 to give us 8,000 different options. There we go. Types of probability. The classical probability is used when each outcome in a sample space is equally likely to occur. The classical probability for an event E is given by PE is equal to the number of outcomes in event E divided by the total number of outcomes in the sample space. So I think of this as your question or your part divided by your whole, your total. Example 5. You roll a 6-sided die. Find the probability of each event. Okay, so a regular die, 6-sided die, we have 1, I think this 2, 3, right? And then you have 4, 5, 6 different options. You have dots to represent those numbers. What's your probability of rolling a 3? So how many ways can you get a 3? Well, if it's only one die, how can you get 3? You can only get 3 by getting that one die to be a 3. So it'd be 1 out of, what are your total number of options? You have 6 different options. 1 out of 6. That's it. Now, because we want a probability, we want to give a decimal answer. So just punch this in your calculator. 1 divided by 6. 1 division by 10 6. You'll get 0.167. 2. Rolling a 7. Okay, well, how many ways can you get a 7? Well, there's no 7, right? Our options are only 1 through 6. So our probability would be 0 out of 6, which is just 0. Third one, rolling a number less than 5. So if I look at my options, I have numbers 1 through 5. The numbers that are less than 5 are 1, 2, 3, and 4. So those are 4 numbers. So P less than 5. I have the numbers 1, 2, 3, and 4. So those are 4 numbers out of the 6. 4 out of 6. If you want to reduce your fraction, that's short of 3. However, if you're punching a calculator, that gives you about 0.667. Next, definition of empirical probability. Empirical probability is based on the observations obtained from probability experiments. The empirical probability of an event E is a relative frequency of event E. So, just as before, it's your part divided by your whole, or your total number. Example 6. A company is conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. The pie chart shows the following results. What is the probability that the next adult surveyed read only print books during the last year? Okay, so we know the number of adults surveyed, right? 1,490. And that makes sense because that's made up of all of our numbers so far. So I have 395 for read no books plus 578 for read only print, 426 for read both online and digital, and only digital is 91. If we add them, we get 1,490. That's our total, right? Our amount surveyed. Our question asks for what's the probability that they read only print books. Only print books, well, that's right here. That's 578. So 578 divided by 1,490, that gives us, we punch into a calculator, and you can round. So it's about 0.388. Definition of law of large numbers. As an experiment is repeated over and over again, the empirical probability of an event approaches the theoretical actual probability of the event. An example of this is tossing a coin. We can understand that the probability of getting heads or tails is about 50%, half tails, half heads. But we toss a coin a couple of times, you might get a result that's not 50%. You might notice you get heads more often than tails, for example. However, if we continue this experiment for a much longer space, you would see that 50% is our probability. That's the law of large numbers. Definition range of probability rule. The probability of event E is between 0 and 1 inclusive. That is, P is less than or equal to PE less than or equal to 1. This is about what is the most you can earn or have something be. So 100%. And 100% in decimal form is 1.0. So a probability must be greater than 0, meaning no negative is not an option, and the maximum number of the sum of probabilities cannot be more than 100, or 1. This is the range of probabilities. This number line also helps determine how we can relate a probability, or refer to it in actual words. So 0 is impossible, 0.25 is unlikely, 50% is an even chance, 0.75 is likely, and 1 is certain. So it's just saying all your probabilities must be between 0 and 1. This is important. They cannot exceed more than 1. And it can't be less than 0. Complement events. No, this does not relate to how your hair looks or how cute your shoes are. This means not it. Well, what if we say the probability of rain is 60%? Then the probability of not rain is 40. It's basically in a chance the opposite of 100, or 1 minus, or if you're talking percents, 100 minus. It's the opposite of it. Definition of complement of event. The complement of event E is a set of all outcomes in a sample space that are not included in the event E. The complement of event E is denoted as E prime. The Venn diagram illustrates a relationship between the sample space and its complement. So if this circle is E, then the opposite of it is everything that's not it. So its complement in our sample space would be everything else. Let's do an example. An access code consists of 3 digits. Each digit can be numbered from 0 through 9, and each digit can be repeated. Okay, so we did a problem that's kind of like this. So we see we have numbers 1 through 9. That's 10 different options, and we have 3 digits to fill out. A. What is the probability that a random selection of correct access codes on the first try? Okay, we can randomly create a correct access code. Well, our first try would be 1 out of 10. Our second try would be 1 number out of 10. Our second number would be 1 out of 10. So a probability of this would be 1 out of 1,000. If we want a decimal form, that would be 0.001. Now for B, find the probability of not selecting the correct access code in the first try. So if this is finding the correct access code on the first try, not finding the correct access code will be the complement. So it'd be everything else. So 1 minus. So I have 1 minus 0.001, and that gives us 0.99. So you can see how probable it is to not get the correct access code on the first try. Okay, that's it for section 3.1, Basic Concepts of Probability and Counting.